This is the key to Sage and Scribe Gas Problem Set 3. So we're going to start with number 1. It says a car has a volume, internal volume, so this is my V1. If I drive my car into the river and it implodes, what will be the volume 2 of the gas when the pressure goes from P1 to P2? Now, if you haven't noticed, the pressure units are different, so I'm going to have to convert either one to make sure I get the same consistent units. I have chosen, and you can choose otherwise, to convert 142 kPa's into millimeters of mercury. And I'm going to use dimensional analysis. There's 2 converters that I'm going to use. One is converting kPa to ATM, and I know that 1 ATM has 101.325 kPa. And then I'm going to take the ATM to cross cancel it and convert it to millimeters of mercury. And in doing so, I get 1,065 millimeters of mercury. Now this is my P2 because originally the 142 kPa that you see here is now really equivalent to 1,065 millimeters of mercury. So this is in fact 1,065 is my P2. So now I'm going to use Boyle's law. This is a Boyle's law problem. So P1 is 760 millimeters of mercury. P2 or V1 is 12,000 liters, and then P2 is 1,065 millimeters of mercury, and I'm trying to solve for V2. And so V2, when I solve for it, is 8,600 liters. Now let's jump into number 2. Now, number 2 must be a gas stoich problem, and there's a couple of hints. I see here the equation, a balance equation. Second hint, I see that I'm given amounts of water, and I'm asked to find another substance, nitrogen. And the only link between water and nitrogen is this balance equation. And the link is the 2-to-1 ratio that's between the two here. Now, I'm going to note that we're at STP. So anytime I have STP, I can use molar volume, which is 22.4 liters in 1 mole of any gas. So I'm going to start with what I'm given. I'm given 50 grams of water. And I'm trying to get to ultimately nitrogen. So in order to do that, I need a mole ratio. In order to do mole ratio, I need to convert my grams of water to moles. So grams on the bottom of water, mole of water on the top. 1 mole of water has 18.02 grams, according to the periodic table. And so now I need to cancel my moles of water so that I can try to get my moles of nitrogen. So now I'm really leading into getting nitrogen, and the mole ratio between the two, according to the balance equation, is a 2-to-1 ratio. And that's precisely what I'm going to do for the mole ratio fraction here. So for every 1 mole of nitrogen, there's 2 moles of water vapor. And from there, I am then going to use molar volume, because I know that in 1 mole of nitrogen, of any gas, including nitrogen, there's always 22.4 liters. And that will finalize my problem. I will get 31.1 liters as my final answer. Now, I also like to cross-cancel the units so we can see how the units work out. Grams of water cross-cancels. Moles of water cross-cancels. Moles of nitrogen cross-cancels, leaving me with liters of nitrogen as my ending unit. Jumping down to the third problem, now we're looking at a sample of nitrogen is is inside an expandable container at, looks like my T1. The container is then placed into an oven whose temperature is T2 and expands to a volume of, so here's my expanded volume of V2. The pressure inside the container when it was originally 20 degrees Celsius is my P1. What is the new pressure, P2, of the nitrogen in kPa? So I am going to set the problem up. I forgot to put my V1. So here's my V1. Now, let's go ahead and set the problem up. It looks like there is volume changing, V1, V2, temperature changing, T1, T2, and thus pressure changing, P1, P2. So it looks like I'm using the combined gas law. So I'm going to set up my combined gas law. So one side equaling my other side. So my P1 is 3.00 ATM. My V1 is 30 liters. My T1 is 293 Kelvin when I add 273 to 20 degrees Celsius. My P2 is what I'm trying to solve for. My V2 is 100 liters. My T2 is in fact 50 degrees Celsius plus 273 gives us 323 Kelvin units. And once again, I like to cross multiplication or butterfly method to solve for my P2. And in solving for my P2, I do get this value of 0.992 ATM. Now remember that I need my value of pressure in kPa. So if you go back to the question, it says, what is the pressure of nitrogen in kPa? Currently, I have my pressure in ATM, so I'm going to have to do my dimensional analysis to convert my pressure unit. 1 ATM, cross-canceling those two units, will give me 101.325 kPa. And so when I multiply those two values, I then get 101 kPa. All right, moving on to number 4. In number 4, it says ethylene burns in oxygen to form carbon dioxide and water vapor according to this reaction. Okay, so you and I are thinking the same, hopefully. This is a gas stoich problem. It looks like a gas stoichiometry problem. But now, if you read the problem carefully, you'll notice that you're given liters of ethylene and liters of oxygen, and you're asked to find grams of water. So you're given both ethylene, which is C2H4, and amounts of oxygen. So if you guess it right, it is either one of these reactants, ethylene or oxygen, will limit how much water will form. So we're going to have to figure out the limiting reactant. And if you recall, we're at STP conditions, so temperature and pressure are constant, so the volume is to be treated as though it is kind of similar to moles. So, like any limiting reactant problem, we take our amounts, 1.25 liters of ethylene, and we divide it by its coefficient, which is 1. Likewise, we take 3.00 liters of oxygen and we divide it by its coefficient, which is 3. Now, in doing so, you'll notice which of the two values would be lower in value. So from there, you can see that this gives you 1.25 when you divide it by the coefficient of 1, because there's one coefficient here. 3 divided by 3, which is the coefficient 3 here, is going to give you 1. So this is 1.25, this is 1. Which one's the lower value? And you're right if you said it was 1, which is oxygen. So really, your limiting reactant is in fact oxygen. So this is what we're going to focus on. Here's our LR. So we take what we originally have of our oxygen, which is 3 liters of O2, and we are really trying to get to water. So we mole ratio or volume ratio this because we're at STP, so temperature and pressure are constant, so that you can say that volume and the volume of both oxygen and water are proportional to the mole ratio. So there is, for every 3 oxygen, there is 2 liters of water formed. Now I don't want liters, I want it in grams of oxygen, so I really have to convert this to moles. And I know that 1 mole of water has 22.4 liters of water. So this is only at STP conditions. Sorry, I'm going to write it above here because I'm going to need a little room on the top. So this is only true at STP, and we are at STP. So then we take our mole of water and convert it to grams of water. And so we use molar mass from the periodic table. And that will give us our final answer of 1.61 grams of water. Now notice how the units cross-cancel. Liters of oxygen cross-cancels. Liters of water cross-cancels. Moles of water cross-cancels, leaving us with our grams of water in the end. Now I'm also going to show you how to do this problem using converting your liters of oxygen to moles right away. So let me show you how they both end up pretty much with the same answer in the end. So here we have 3 liters of oxygen, and we're going to ratio to convert first 22.4 liters of oxygen to moles right away. So 1 mole of oxygen. And then I'm going to mole ratio the oxygen to the water. And the ratio is a 2 to 3 ratio. And once again, I do the last conversion, which is moles of water to grams. And notice how the mathematics ends up being the same. So the mathematics here is pretty much the mathematics here. So whether you convert your liters of oxygen to moles right away and then do the mole ratio, or you do a liter to liter ratio and then convert your liters to moles, it really is the same steps, but just one conversion factor being used earlier than the other. So that ends this session.